Okay, so the capacitance is Q over V. Units are farads. What is a farad? Just look at the equation here. It's a coulomb per volt. Okay? And it's a large, large unit. So your typical values are much smaller. Okay, so for a parallel plate capacitor, the capacitance is going to be a constant times the area of the plates divided by the distance between them, the gap. And we've talked about that already. Right? You'd expect as the area gets bigger, you'd expect the slope to be bigger, right? The charges, the same voltage can move more charges over. And when the distance becomes bigger, it becomes harder and harder for the same voltage to move the charges over because it's moving them, it's doing more work in moving them. Oh, another application is tuning. Remember we talked about filters, right? These signals that can get through certain frequencies. You can combine a high pass and low pass filter so that only a particular frequency makes it through. That's how the radios in your car work, right? You want to tune the circuit so that it responds to a particular frequency because the antenna, when you're driving around, the antenna in your car is getting hit with every frequency, right? Every radio station. And there's a lot of frequencies out there. For a while, I tried to, you don't realize how many radio stations there are, but I got one of these little devices. I could play my iPod in, what would it do? It would play my iPod through my radio in the car. Have you seen these? But you have to tune the radio to a station where there's no signal. Well, in a city, good luck finding a station. You go 96.1, 96.2, they're all taken. Maybe out in the middle of nowhere you can find a gap and tune your radio where there's no signal. But they're all there. So what do? You have to tune the car radio so it responds exactly to the frequency you want, not to the other frequencies. Well, what do? You have a capacitor. It's an RC circuit. We'll learn about those shortly. But you change the capacitance. How do you do that? There's a picture in the book of one. But you've got metal plates that can overlap in different ways. Let me just put it on. You have a variable capacitor like this. The metal plates can... you can change the overlap. So you turn this knob, and these plates, they kind of sink into each other or not. So you're changing the surface area. As those two sections mesh together, you have lots of surface area. And you get them to come apart, you just have a little bit of surface area. So you're changing the capacitance by changing how much overlap there is between those two metal plates. In this case, there are lots of metal plates overlapping. But you can change the capacitance by turning the dial, and that changes, this is for an analog circuit, of course, that changes the capacitance value, changes how the circuit responds. We'll learn about RC circuits later. But, and then these are all kinds of different capacitors here. These will use a lot of things that look like this in lab, little tiny ones, and I showed you some bigger ones. But they have specific purposes, and then they're designed for those purposes. Sometimes you need small ones, sometimes you need big ones and big power supplies. Okay, so another thing we can do that's kind of interesting is we can take this capacitor, we can take these metal plates. Oh, first of all, the capacitor doesn't have to be parallel plates. It's just that's the most common, and it's very easy for us to analyze. So that's typically what we use, is the parallel plate capacitor. But you could have two spheres. You could have some kind of sphere, conductive sphere with some charge on it, and then inside of another conductive sphere with some charge on it. As long as the two conductors are not touching each other, you can separate charges between them, right? That could be a capacitor. Or you could have a cylinder. Inside of another cylinder conductor, right? So you can have, that could be a capacitor also. So there are other types of capacitors. It's just that parallel plate is the most common. Okay, so as long as they're not touching, you can separate charges. We can make it into a capacitor. These are conductive plates. All right, so another thing we can do, we can take our conductive plates right, we hook it up to a battery. Charges move, the electrons move to this plate. The protons are left behind. We get this charge separation. Now there's an electric field between those plates. Looks something like this. This assumes we've got a vacuum between the plates, or maybe air. Air acts very close to a vacuum. Now, if we stick another material in there, it has to be an electrical insulator, or it's not a capacitor anymore, right? If you electrically connect those two plates, those charges are going to move, and you're not going to have any charge separation anymore. So it has to be an insulator. If we stick an insulator in there, and the fancy word we use is a dielectric. Okay, we've got our positives and our negative plate. And now we put an electrical insulator in there. Let's see, I'll make it green. What happens in our insulator? Let's remember back to our wall and our balloon. What happened in the wall? The electron cloud can shift a little bit, right? The electrons are tied to the molecules they're with, but the cloud can shift a little bit. And in this case, the cloud shifts. So the molecule, that's the molecule right there that makes up the surface of the wall. The electron cloud shifts a little bit, and the surface actually becomes slightly negatively charged. Opposites attract, the balloon sticks to the wall. So what happens in here, there's an electric field pointing to the right. So that means the electrons are going to get shifted to the left. So I'll make my atoms here, my molecules, I'll make this 3 molecules across. So the electron cloud shifts a little bit on this one, and on this one, and on this one. Each molecule, the electron cloud shifts a little bit. And in the center, everything kind of cancels out. In the center here, everything sort of cancels out. And what you're left with is positive surface here and a negative surface there. And what does that do? That creates an electric field in the opposite direction. You see that? So what we had here, I'll draw it in blue. We had the electric field from the capacitor, right, going this way. E from the capacitor plates. And now we have an electric field, I'll draw it in red, a smaller one in the opposite direction from the surfaces of the dielectric. So what we care about is the net electric field between those plates. What happens here is it gets reduced. And it's a vector, right? Because the red one points in the opposite direction, it's reduced now. And if the electric field is reduced between those plates, it doesn't take as much work moving the charges from one plate to the other, and we can move more charges. With the same battery. So that means it increases the capacitance. So C, the capacitance, is a constant times the capacitance without. That's the capacitance, without the dielectric. And that's the dielectric constant.